All right. Thank you. I was muted for some reason. We got a couple of people who needed to come in. Let's bring it in again. Let's let them join. And what I'll do is I'll rehash what I was talking about, because obviously nothing was heard, obviously, because I was muted. Okay, we ended up in chat on this slide 27. We've been talking about the 6 different types of chemical reactions. This is one type. This is what is called the double displacement reactions. And as I was stating, without you guys hearing, because I was muted, is you ask yourself, well, how do I identify that I'm dealing with a double displacement reaction? You look at the reactants. What you're finding here is you got 2 reactants that in both cases are soluble based on the solubility rule. They're both soluble, okay? If you recall in the lab where you were doing different reactions, you may have had one or two that you mixed together and you form a precipitate, okay? That was a double displacement reaction. Now, in both, so to recognize this, I got 2 reactants that are soluble, okay? I'm going to put them together, and since they're ionic compounds, they're dispersed, they're soluble, disperse 100% in solution, and when you mix them together, just by the arbitrary mixing together, the cation would then combine with the mu anion, okay? In this case, the lead 2 ion. And I know it's lead 2 because it is bonded to 2 nitrates, and I know that each nitrate's a -1, so that must be a lead 2 ion. So now the new product is lead iodide, so I need 2 iodides. So there it is, PbI2. Then the other corresponding combination is the potassium and the nitrate. Now the potassium, I know it's a +1. The nitrates are -1, so it's a straightforward 1-to-1 combination. So the formula is a KNO3. So those are the new products, okay? Now, before I go any further, all I got to do now is to check the solubility, because if they're not soluble, then I don't have to bother. If they're both soluble, the new products are soluble, I get a no reaction. Then I don't have to bother with balancing the reaction. Okay, so let's look at potassium nitrate. Now we learned from the solubility rules at number 3 on the solubility column right here, that all nitrate ions, regardless of what they are bonded to, whatever metal they are bonded to, are soluble. So that tells me that potassium nitrate is soluble. Furthermore, we're dealing with potassium, and that's number 1. Again, it's like a double whammy here, because I got the nitrates that are always soluble, and then the compounded with the fact that the big 4 there, lithium, sodium, potassium, and ammonium, whatever they're bonded, those cations are bonded to is soluble. So potassium nitrate is soluble. We got an AQ. The lead 2 iodide. Well, we look at number 4. Normally, number 4, the iodides, in fact, the bromide and the chloride, are soluble, normally, unless they're bonded to these 3 heavy metals: silver, mercury, and lead. So in this case, it is bonded to lead, which means that we have lead iodide is classified as insoluble. We put an S there. That tells me that we have a positive reaction, okay? Positive reaction, and now I can balance it. So let me erase all this other stuff. Keep in mind, what I did first is I put the reactants in ionic form, in ions. I can put the products together in the correct ratio, okay? So I can erase all this now. There's my reactants up on top, okay? And now I can sit there and balance it. All right, so I got two either way. I got one lead on the reactant side, one lead on the product side, so we're good to go. One potassium on the reactant side, one potassium on the product side. However, there are two nitrates on the reactant side, okay? And so there's only one on the product side. So if I put a 2 in front of potassium nitrate, that balances my nitrates. But in doing that, that kicks my nitrates up to 2, my potassium, I should say. All right. Well, no problem. I go to potassium iodine, I put a 2 in front of Ki. Okay. That balances out my potassiums. And in doing that, it also happens to balance out my iodides because there's 2 iodides on the product side. Now I got 2 iodides in the reactant side. So I have a balanced chemical reaction, okay? All right. So let me clear this up a little bit. That's the reaction right there, okay? All right, here we have another double displacement. How do I know that? Well, I got 2 reactants with 2 reactants that are compounds. Furthermore, they're both of them are soluble, okay? So what I'm gonna do first, like I did before, is I'm gonna break them down into ions. So I got barium chloride. I know that barium is a group 2 metal, so it will have a +2 charge in ionic form. Furthermore, I know that the chlorides are -1. All the halogens always a -1. There's 2 of them, okay, which verifies that potassium is a +2. All right, silver is always a +1, if you recall. It's one of the sweet 16 that we know their charge 100% of the time, okay? And then the nitrates, like previously, you look in the polyatomic ion tables, it's got a -1, okay? So those are the ions. So now what I'm going to do is we're going to put together the new products and check the solubility as we did earlier. So we have barium combining now with nitrate, okay? Now barium has a +2, nitrate is a -1, so we need 2 nitrates for every barium +2 ion. So our formula becomes BA parentheses NO3 2, okay? Then we're going to put together the silver and the chloride. And it's a simple, straightforward 1-to-1 because silver is a +1, chloride is a -1. And so its formula will be AgCl. And there it is. All right. Next step, check the solubility. Okay, well, barium nitrates, we learned earlier from the earlier example that nitrates, number 3, are always soluble, okay? And so barium nitrate will have an AQ there. It's soluble. The silver chloride, again, we go check the halides, number 4, we can see here's the chloride here. Normally, the chlorides are soluble unless it's attached, bonded with the 3 heavy metals, of which silver is one of them, which it tells you that silver chloride is insoluble, so we put an S because it's a solid, it will precipitate, it gets cloudy in the container, and then if you let it settle or sit there, the solid will settle down into the bottom of the container. So we have a positive reaction, okay? So now I can do what I did earlier. I'm going to get rid of the ions in the beginning. Again, I put them in ionic form first so I can make sure I can put them together properly with the rate ratio in the products, all right? Now my next step is to balance them. So I see here that I have 1 barium in the reactant side, 1 on the product side. I got 1 silver in reactant side, 1 silver in the product side. So The metals are okay. The chlorides, however, are not. You can see that we have 2 chlorides on the reactant side, but only 1 on the product side. So if I put a 2 in front of silver chloride, that balances out my chlorides, but in the process of doing that, it kicks up my silver to 2, okay? So now I go back to the reactant side, and if I put a 2 in front of silver nitrate, that takes care of my silvers. And in the process of doing that, putting that 2 in front of silver nitrate, that tells you now I got 2 nitrates, which is okay because by default, I have 2 nitrates on the product side because it's bonded out to barium. So now I have a balanced chemical reaction. Okay, let me clear it and bring take my stuff off and bring in the equation. Okay, so we got barium chloride plus 2 silver nitrates react to give us 1 barium nitrate and 2 silver chlorides. Positive reaction for a double displacement reaction. Okay, now we have a term for these reactions, and it's a general term. It's called redox reaction. Okay, what's happening here in the majority of these reactions is that one species is giving up their electrons while the other species is gaining the electrons. Okay, and many of the single replacement reactions, the combination, the decomposition, and the combustion reactions are also known as what are called redox reactions. Okay, and redox is a short term. It's a combination for the term of reduction and oxidation. Okay, now what does that mean? Okay, here's reduction and oxidation. If you take the RED, the red from reduction, and the OX from oxidation, you have the term redox. Okay. Now, what this means is the following. Reduction is the gain of electrons. Okay. When a species gains electrons, when an element gains electrons, it is called reduction. For example, the halogens, they're a group 7 element. They need 1 electron. They will gain 1 electron. So what they're undergoing is reduction. Oxidation. So if reduction is the gain of electrons, then oxidation is the loss of electrons. So if you have like one of the metals in elemental form, like say sodium, it has 1 valence electron, it will lose that electron because metals want to lose an electron. And in doing so, it undergoes what is called oxidation. Now, these reactions, the single replacement combination or quote reduction reactions, they occur, the oxidation process and the reduction process occur simultaneously. It's not that one species loses electrons and nothing else happens to the other species. No, they occur together. When one undergoes reduction, something else is undergoing oxidation, okay? Perfect example of that would be your battery. If you're running off a battery right now for your electronics, on that battery, on one side, you got positive side and the negative side. On one side of that pole, a species is losing an electron, and on the other side, the species is gaining an electron, allowing you to create a current, which then powers your electronics. Okay. All right. So another way to say that you lose electrons or gain electrons, personally, I prefer the term you lose or gain electrons, okay? Because then when you start putting charges in there, it kind of gets a little bit ambiguous, not too much, but It gets a little ambiguous, but I'll break it down here because your textbook talks about the charge goes up or the charge goes down. Now think of it in terms of a scale, a number scale, okay? So we have a number scale, for example, and we have 0 right here. And then obviously we get going up 1, 2, and 3, etc. But going down the scale becomes a negative value, right? -2, etc., -3. Okay. And so an element, for example, starts off at 0. Remember that all elements have a net oxidation of 0 because they have an equal number of protons, equal number of electrons. When you lose an electron, they become positive, like the metals do. That means their oxidation number, their charge goes up in the positive direction, okay? Which is up in this direction, and this is in the negative direction. Okay, so your oxidation number, your charge goes up when you lose electrons. So if you lose 1 electron like sodium, you go up through a +1. Okay. Now, if you're a non-metal and you start off as an element, obviously with 0 charge, you're a non-metal, you will gain an electron. Okay, you will gain an electron, and your oxidation number goes down to a -1. Because they're using the term, -1 is much less than 0, okay? So your oxidation goes on, and that's what they're saying here. Reduction, which is the gain of electrons, means that your charge goes down. So you start at 0, and you lose an electron, so you go down in this direction, you have a negative charge, okay? Oxidation is the loss of electrons. And so your charge goes up. Again, if you start at 0 and you lose an electron, your number goes in the positive direction. You have a positive charge, so it goes up. That's what they're using here. So think of the charge going up, charge going down as simply like on the number scale, okay? To help you out with that. All right, so as I mentioned, oxidation and reduction occur simultaneously. It's not that you can have one without the other. It's a balance of charge. It's a balance of energy. It's a balance of nature. One thing is happening someplace. The counters have happening someplace else. Okay. All right. Which is kind of interesting because if you recall when we were talking about the electrons and in the orbits that they exist, we can have 2 electrons per orbit. So like in the S, we can put 2 electrons. Well, it's been demonstrated that these electrons, 2 electrons in one orbit, are actually circulating in opposite directions. So one goes in the positive direction, the other goes in the negative direction. It's just a par for the course of 2 charges having to go in opposite direction, 2 like charges. And it's been demonstrated that if you can change the direction of one of those electrons to go from whatever direction it is to the opposite, spontaneously the partner in that same orbital will flip and go in the opposite direction. Interesting phenomenon. Just the way Mother Nature is trying to balance energy around us. All right, so this again, we talk about charges, and I'm using the term oxidation number, okay? Because simply because when we're dealing with ionic compounds, we do have a full charge, full positive, full negative charge. They come together like 2 magnets coming together. But when we're dealing with ionic compounds, covalent compounds, we're not dealing with a full charge. If you recall, we're dealing with a partial charge, which is related to the electronegativity of the elements that are bonded together. So instead of using the charge, we use the term oxidation number, and that encompasses both ionic compounds and covalent compounds. okay? So oxidation numbers are the same as the charge. Elements in their natural state have a net zero charge, as I've stated numerous times. Equal number of positive protons, equal number of negative electrons, okay? We talked at length about the group 1 ion, which has a +1 oxidation number, group 2 +2, group 3 +3. Recall that these are metals, okay? And metals have the tendency to lose electrons, and therefore by losing electrons, now the next energy level in is full, and that happy magical octet has been fulfilled. Okay, it's all about that octet, trying to obtain that octet. Now, with respect to group 4, to refresh your memory, they have 4 valence electrons. That's the group that where carbons have. Those elements had the capability of, because from an energy perspective, losing 4 electrons or picking up 4 electrons, basically about the same amount of energy. So they had the capability of losing all 4 or gaining 4. So their charge, their oxidation number can vary from a +4 on one end of the spectrum to a -4 and anything in between, okay? And that's unique about these guys in group 4. They have one way to look at it is look at it as they're on the fence, and they can fall left or right depending on the conditions. If they fall left, they're going to be like the metals and lose electrons. If they fall right, they're going to be like the nonmetals and gain electrons. Okay. Now, once we pass the group 4, we enter the domain of gaining electrons. So from 5 to 7, they're nonmetals. They will gain electrons, and in doing so, they now become isoelectronic with the noble gas in front of it. Okay. So group 5 will pick up 3 electrons. Remember, the goal is to get that octet. Think about it. Group 5 has 5 valence electrons. So from an energy perspective, losing 5 electrons and compared to just gaining 3 is a lot more energy efficient than trying to lose 5 electrons, okay? Because in gaining 3 electrons now becomes a lot more stable, okay? And the same is true for group 6. It only needs 2 electrons to become more stable, rather than trying to lose 6 of them, which is from energy perspective, very, very unfavorable. And in the group 7, again, 7 valence electrons, even more so unfavorable to lose 7 as it is compared to gain 1 to get that magical 8. And of course, we know that group 8, the noble gases and helium, which is a duet, that nothing's going to happen. Oxidation number is 0. Their valence shell is full with that 8, except for helium has 2, and it's going to be very difficult and energy inefficient to pull off an electron. It take a lot of energy to yank one off. Okay. Now, also we have, besides group 1, group 2, and group 3 metals, we also include, if you recall, silver always has a +1, zinc and cadmium always have a +2. Remember, they are part of the sweet 16. We have an exact and a constant oxidation number. And that being the case, they don't require Roman numerals in the nomenclature of these metals. That means everybody else, all the other metals, require Roman numerals to distinguish which ion we are working with. Okay. So losing electrons that we talked about, the charge goes up. Okay. So let me put that scale back up. We had a scale like so. We had 0 here, and then +1, +2, +3. Down in the opposite direction, -1, -2, and -3. All right, so losing electrons, so we start at 0. If we lose electrons, okay, our our charge or oxidation number goes up, like the metals. So in this case, we have copper, which has a 0 oxidation number. That's supposed to be a 0. Okay. It's a metal. It will lose electrons. Excuse me. It will lose either 1 or 2. In this case, we're showing it can lose 2. Okay. So in this case, copper is oxidized. Its charge goes up. Its oxidation number goes up to a +2. Okay. Since it is oxidized, it becomes what is called the reducing agent. Okay. The agent that produces electrons that another element will utilize. Okay. Just like a ticket agent. It's a ticket agent is somebody that produces tickets that you're going to use. Okay. So what is oxidized is the reducing agent. Oh. In this scenario, we have sulfur, which is a nonmetal. So it starts at 0. It will gain 2 electrons, so its oxidation number will go down. Okay, because it gained 2 electrons. So in this case, for this reaction, sulfur is reduced, which then makes it the oxidizing agent. Okay, it makes it the agent that will utilize those electrons that the reducing agent produced. Okay. All right. As I stated earlier, redox reactions occur simultaneously. You can't have one or the other. Now, when we talk about what is oxidized and what is reduced, we're always talking about the reactants. We're not talking about what the products are. The products are, it already happened. We're done with it. So we're concerned only with the reactants. And when we look at a reaction, we ask the question, well, what is reduced and what is oxidized? And whatever is reduced, we just say it's either the ion, if you're given an ion in the reaction, or if it's a compound. You give the full name for whatever the compound is. We'll give some examples of that here in a bit. All right, now, with respect to the charges, you got to figure it out. All right, let's take a look at this. So in this example, we have copper +2, so it's not a compound, it's just the iron. And it's reacting with, iron. Just give me a moment there for a second. Yeah. Okay. Now, in this type of reaction where we have the copper ion plus the metal or iron, do you know what type of reaction that is? Of the six, what type of reaction would this be? What do you guys think? They could have written it in this form. They could have said, let me make sure I got it. They could have said copper 2 chloride plus iron reacts to give you the copper plus iron 2 chloride. They could have written like that. Oh, that's a 2 there, not a 3. Okay, but they decided to write the ions. But it doesn't take away from being able to recognize what type of reaction you are working with here. Okay. Well, remember how we did that in the lab? We went through till we became more comfortable. We thought about all the 6 reactions that we have available. Obviously, it's not an acid-base reaction, right? Because there's no protons here, no hydroxides, so we can eliminate that. All right, it's not a combustion reaction because combustion reactions, we're dealing with hydrocarbons and oxygen. That's not a factor here. Okay. It's not a double displacement reaction like the examples we did before earlier. There's like 3 examples where the reactants, as I stated, were both compounds and soluble in water. In this case, we have iron metal, which is not a compound. Okay, so we can eliminate that. All right, so I made 3 of them for you. So what type of reaction would this be? It's a typical type of question one could be asked to determine what type of reaction it is, and then
Will it be single displacement?
You got it. It is definitely a single replacement. If you look at the activity series, you will find that iron is a lot more reactive. It's more reactive than copper. Okay, and that being the case, iron is not in ionic form, so therefore reaction proceeds, and there's an exchange now between copper ionic form and now it is copper in elemental form. Okay. All right, so here's one way to produce copper metal if you have a lot of copper in solution is to use iron. It will exchange position. You can produce copper pull it out of the solution. All right, in this particular example, let me clear this up. We see that copper went from a +2 oxidation state to a 0, okay? And so its charge went down. It went from a +2 to a 0. So in going down, think about it. How do I get a +2 equals 0? Well, I add negative numbers. I need a -2. So a +2 plus a -2 equals 0. So what is negative? That's electrons. So what happened was that copper +2 must have gained 2 electrons. Okay, and it underwent reduction. It got reduced because it went from a +2 to a 0. Okay, now look at iron, and we're just looking at the reactants. Iron went from a 0 charge because it's an elemental form to a +2. And so in that case, the charge went up, the oxidation number went up. So in doing that, it must have lost 2 negatives. So it lost electrons, so it underwent oxidation. So iron underwent oxidation, copper underwent reduction. Okay, which makes the oxidizing agent the copper ion, and the reducing agent is the solid iron. Okay, remember, in identifying what is oxidized, what is reduced, we're only concerned about the reactants. What happens in the product side, that's it. You're not going to do anything else. That is the result of what happened with the reactants. Okay, here's another example. We have copper nitrate, specifically copper 3 nitrate. Okay, what is the oxidation state of what did I say, copper? Nobody caught that? What is CO?
Cobalt.
Cobalt is actually, now can you look at that formula and tell me what is the oxidation state of cobalt nitrate? Because it's attached to nitrate. What must cobalt be in this oxidation state? What do you guys think? What do we know about the nitrates, the NO3? What is each one? What is its oxidation state? Nitrates. Look at your polyatomic ion table. Each nitrate is a -1. Okay, we got 3 of them. What does that mean for cobalt? What must cobalt be?
+3.
You got it. Okay, it's got to be a +3. Now, in this reaction, it goes from a +3. You look on the far right, now it's a solid. It's no longer cobalt nitrate. It's simply cobalt all by itself, elemental cobalt. So elemental cobalt has a 0 charge, oxidation number, because an equal number of electrons, okay, and an equal number of protons. So it went from a +3 to a 0. Platinum starts off as a 0. Okay, but then reacts with the cobalt nitrate. So platinum here is a lot more reactive. You got a single replacement reaction going on again, and exchange places with the cobalt. So now we have platinum nitrate. Okay, so its oxidation number went from a 0 to a +3. That means it underwent oxidation. Platinum PT went from 0 to a +3. It lost 3 electrons, whereas cobalt-3 nitrate underwent reduction because it starts off with a +3 oxidation state and it goes to 0. In order for that to happen, it must gain 3 electrons. Okay, and so platinum underwent oxidation, cobalt-3 nitrate underwent reduction, and then there's the corresponding agents for each one. All right. Of course, I just told you what this is. Cobalt-3 nitrate is the Roman number 3 nitrate for cobalt for that compound. All right, there are YouTube videos by Dr. Kim. You know, you need additional information or alternative listening to this topic. So, you know, we did time watching. And that being said, summary, to summarize this particular chapter, you know, be familiar with the solubility rules, okay? So be able to look at a reaction and determine, well, first of all, determine the compound itself. Is it soluble or insoluble? Okay. And if it's insoluble, then we use the physical state of S. Now, bear in mind, even though it's classified as insoluble, remember we were talking about the weak electrolytes and strong electrolytes, okay? Even though it's classified as insoluble, there's always a little bit of ions in solution, but they're a weak ions, so it'd be weak electrolytes for those compounds that are classified as insoluble, okay? And those that are classified as soluble are very strong electrolytes because essentially they dissolve 100% or close to it. The activity series, yeah, using the solubility rules, we use that for the double displacement reactions to predict what the products are. Because all we do in the double displacement reactions, and we'll reemphasize this, how do we recognize them? By looking at the reaction, we look at the reactants, and we normally see we got two different compounds that are soluble. We have an AQ in there as a subscript, and mix them together, and then the corresponding positive and the cations and ions exchange with each other, and then we look at the products, the new products, and determine from the solubility rule if anybody is insoluble. If one of the products is insoluble, we got a positive reaction. If both new products are soluble, then it's a negative reaction. Okay, nothing happened. All right. The activity series, we utilize this to determine the single replacement reactions. And what we're doing here is we're looking at two metals. One metal is in elemental form. The other metal is in ionic form. We look up the activity of those two metals, determine which is more reactive of the two metals, regardless if it's in elemental form or ionic form. We look and see which is more reactive. Once we determine which metal is more reactive, then we look to see if the most reactive metal is in ionic form. Is it a compound? If the most reactive metal is in a compound already, then we get no reaction. Okay. If it's not, then the metals exchange places, we have a positive reaction. Because the driving force is this between the two metals. They both want to get octet, but when we compete two metals with each other, the most reactive metal is going to win. Okay. Okay. I gotta get this phone call real quick. It's important. So give me 5 minutes. Okay, I'm back. Sorry for that. I needed to answer that. Anyway, let me summarize this. I just finished talking about the activity series. That's for single replacement reactions. Recall these solubility rules and activity series are found on the periodic table. Okay. With respect to the different reactions that we talked about, recognize and balance combination reactions. How do I recognize a combination reaction? 99.9% of the time, you have two elements coming together to form a compound. Okay, let me repeat that. At least two elements, two different elements coming together to form a compound. With respect to decomposition, that's the breakdown of a compound. So you have a compound, which something is done to it. It could be anything. And then it is broken down back to their respective elements. Okay, it's the opposite of the combination. Okay, single replacement reaction. How do I recognize that? Look at the reactants. Normally I have one metal, which is an elemental form. It's there all by itself. And then have another metal that's in ionic form. It's a compound. Okay. And then we use the activity series to determine if there's going to be exchange of the position. So if the metal that's in elemental form is more reactive than the metal in ionic form, they're going to exchange positions and the element is going to become ionic. Okay. With respect to balancing, combination, decomposition, single replacement, these reactions are pretty small. They're not very large reactions that they could be balanced for essentially trial and error. We put a number here to see how that fits back and forth. We go back and forth, product reactant until we get the right coefficients. Okay. The double replacement reaction, again here, we how to recognize a double replacement reaction. I'm working with two aqueous compounds. Okay, they're soluble. Mixed together, they exchange partners, if you will, and then depending on the solubility rules, if one of the new products is insoluble, we have a positive reaction. If both of the new products are soluble, it's a negative reaction. We call that this type of reaction also a precipitate. An acid-base reaction. I got two things. We're going to deal mostly with the Arrhenius definition of an acid, and that is any compound that produces a proton. That's an H+. 99% of the time, it's written with hydrogen first, followed by whatever. It could be a chloride, it could be NO3, SO4, it depends, it makes no difference, but hydrogen's first. That's a good indication you're dealing with an acid. With the exception, H2O is not an acid. By default, they write it like that in that manner with hydrogen first. The base, you're always going to find hydroxide. The base is any compound that produces hydroxide. the key ingredient, key in reactants here is the proton and the hydroxide that react together to form water. Okay, to balance these type of reactions, follow the protons and follow the hydroxides, and everything else will fall into place. Okay. Keep in mind too that if you look at the acid and it has 3 protons, 3 hydrogens, you're going to need 3 hydroxides. So, and if that's the case, you're going to make 3 waters and 3 hydrogens, 3 protons, 3 hydroxides, you make 3 waters. Combustion reaction, the only type of combustion that Chem 130 is going to deal with is the combustion of hydrocarbons. Those are compounds that consist of nothing but carbon and hydrogen, okay? And then oxygen is one of the reactants. So the question would be, it could be, write the reaction for the combustion, keyword, the combustion of a given hydrocarbon that be written out. Could be anything, propane. Well, hopefully you should know that for anything to burn, I need oxygen. So oxygen's a reactant. And the combustion of hydrocarbon for Chem 130 only produces 2 products, carbon dioxide and water. Okay, that's it. So you got the hydrocarbon plus oxygen, arrow, producing carbon dioxide and water. How do we balance these? Balance the carbon first, followed by the hydrogen, and then at the end, the oxygens. Okay. For like we just finished talking about, for most of these reactions, we call these a redox reaction, because what's happening is somebody is oxidized, which means loss of electrons, undergoes oxidation, and the other compound is undergoing reduction or reduce, and that's the gain of electrons. Keep in mind that this occurs simultaneously. There isn't anything that we're aware of where oxidation occurs all by itself. There's always a corresponding reduction occurring. All right, that in mind, we are done with chapter 10. Okay. Any questions about that? All right. Which brings us to chapter 11, of which the Chem 130 here, we are talking about giving you the tip of the iceberg of thermodynamics. Thermodynamics is a whole field all by itself of chemistry. It's under the realm of what's called physical chemistry. If you think about it, just looking at breaking down the name, you got thermal, which is dealing with energy / heat, and the dynamics of what's going on with the compound, or 2 or 3 compounds. What are dynamics? What's going on? So we got, and how is the energy affecting the dynamics of a reaction? Okay, so that's thermodynamics. So we're going to talk about the tip of the iceberg. And it's very short chapter, very short. Okay. Now, you may have maybe gave us some thought. I don't know, but when we were doing in the lab these different reactions and you're putting reactants in there, things happen or did not happen. Okay. But if you think about it, when something did happen, you got a positive result. Certain things had to occur for it to get a positive result, okay? And we call that the collision theory, meaning that if we have 2 reactants denoted here on the far left, we got 2 diatomic molecules coming together, okay? Certain things have to happen, and if things don't happen, then we get a reaction. So notice here, we got the 2 reactants coming together. Let me change this color a little bit. We got 2 reactants coming together, okay? And eventually we're going to make 2 new products. And what's happened is this bond between the 2 yellows are broken, and the bond between the 2 reds are broken, and we create 2 new bonds to make a compound. So we start with two elements, two diatomic elements, and we create two compounds. We go through this middle state, okay? We go through this middle state where at this middle state, there simultaneously things are being broken right here. And then bonds, I shouldn't say things, but bonds are being broken and then bonds are being formed. Okay, we call that intermediate state, what we call a transition state. Okay, so it takes a certain amount of energy to get to that transition state. We think of it as going on top of a hill, and then actually, once you reach that top of a hill, which requires an X amount of energy, then you get the product. Okay, so it takes a specific amount of energy to get to the transition state. Second of all, it has to have, these reactants have to have the correct orientation. Because without the correct orientation, you can see that if they don't line up properly, the bonds are not going to be broken and formed. So there's a lot of things that have to come into play for a reaction to proceed. You know, I equate this to shooting pool. If you ever played pool, you know, and you're trying to get a ball into the corner pocket, and you're on one side of with the cue ball, you're on the other side of the table. You've got to have the right angle. Okay, you got to hit that cue ball with the right angle to make it to the corner pocket, or for that matter, any pocket. Not only that, you got to hit it with the right amount of energy. If you don't hit it hard enough, that ball is not going to go into that corner pocket or whatever pocket you're shooting for. Or if you hit it too hard, it might just shoot off the table. Okay, so a lot of factors have to come into play for you to get that ball into whatever pocket you needed to get. And that's what's happening here with chemistry. We got to have the correct orientation. We got to have the correct amount of energy to get the product. Okay. Let's clear this. All right, so we're going to have successful collisions. Now, to do that, we have to increase the number of collisions if we want a reaction to occur. So obviously, we need more collisions to make sure we get product. Now, we also have to have enough energy. It's a very specific amount, a name for this energy is called activation energy. Okay, so to increase the number of collisions, you need more collisions. So you might do that by maybe adding more of your reactants. You know, if you add more reactants, then you have a better chance of reactants coming together to make products. Also, you got to have enough energy. So you have to maybe put energy into the system. Okay, and with that, you know, the molecules have to orientate correctly. What can we do with the orientation? Well, we're going to talk about that a little bit, is we can put things in there called catalysts. Catalyst does help occasionally. The catalyst is something that we put into a reaction that in itself does not have a direct effect as far as interacting with the reactants, but they may reduce the energy of activation, meaning that the energy requirement now is lower, or they may put the reactants together so the orientation is correct, so they can get their products made. A lot of things occur. This reaction dynamics can be very complicated, but it does give us a lot of information. So anyway, increase the more collisions, we just add more material. That's one way to do that. Okay, we can increase the temperature, but we got to be careful with that. Okay, yeah. Normally what happens for every 10 degrees of temperature increase, we increase the rate of the reaction. The rate of the reaction is how the reactants get together to make product. But if we put too much heat, we can cause either the product or the reactants to decompose. So we got to find that happy medium. So, chemistry is not as simple. We put stuff together and go with it. I personally spent a couple months working with a reaction before I can get the products that we were trying to get. And we had to play with all the different variables. So finally we got what we were trying to get. So increasing the temperature, that makes the molecules move faster, which increases the collisions, which increases the probability of having the right orientation. And the energy also then make sure that you have enough energy to overcome that energy of activation. Okay, temperature has a lot of things that help it along, but at the same time you better be careful. Or as I mentioned earlier, we can add a catalyst. A catalyst, what that does is a species that will lower the energy of activation. And so if you have to, for 100 units, let's say, just for argument's sake, that this reaction requires 100 units of energy, okay? Well, catalyst may fix it, so maybe it just now needs 10 units of energy. Whereas before it would require high temperature for it to occur. Maybe now you could have it occur at room temperature or much lower temperatures, okay? Also, too, some catalysts will actually grasp the lock. Now I want to say lock it in, but put the reactants in such a position that now the orientation is correct, and increases the chance of the reactants to come together with the right orientation to produce the product. Okay. All right. So energy of activation is the minimum amount of energy needed to have the reactants become products. Okay. Anything less than that, the reactants just don't go over the hill, over this energy. Think of this energy of activation as trying to overcome this hill. And we're going to have profiles of that here in a second, so to demonstrate that. Equilibrium reactions. Well, basically all this we're going to say about this is that the forward reaction rate, see, all these reactions occur at a rate, certain rate, that the forward reaction rate is equal to the reverse reaction. And, some of these reactions, I should say not reactions, like the acids that were weak, where we show we have the acid and they would dissociate to the corresponding ions. But we had a double error for the weak ones, meaning that the bulk of them were still as reactants, and we have a few ions out there. Okay. A good example of an equilibrium reaction is a soda pop container. It's not a reaction, but how to demonstrate an equilibrium reaction. If you take your soda pop, cap it tight, and you shake it, all that carbon dioxide comes out. So you disturb the equilibrium. You might move it over to the right. Now, if you let that container, the soda pop, sit there, obviously, now you can open the container. And what happens is it shifts. The equilibrium went from the right, now it's going back to the left until it finds that balance it needed. Okay? All right, so let's talk about these energy profiles. But we'll come back to this here in a second. Let me share with you a whiteboard. Okay. Now, if we were to follow a reaction and collect data points, we would have a graph that looks, let me make it a little bit better here. We will have a graph that looks something. Cool. Something like this, okay? And so here on the x-axis, this will be energy units. Okay, and we're just gonna put arbitrary units here. So, 10 energy units, 20 energy units, 30, 40, 50, 60, etc. Now, in this, that's the Y direction. In the X direction, I don't know, we just call it the reaction coordinate, but it could be time. We just follow the reaction, take a snapshot, measure the energy, collect the data point. Let it follow a little bit longer, stop it, take a snapshot, if you will, or do an analysis, find out what the energy is at that level. Okay. Now, we can start off, for example, where the reactants are X amount of energy. So you can label that R. That's where the reactants are. And they have an X like dotted line, which let's say it starts off at 30 energy units. Okay. And so we let the reactants do their thing and we take a snapshot, if you will, as the reaction proceeds and we collect our data. We're going to end up with a graph that looks something like this. Well, a little bit straighter than that. What I have at this side is my products. Now, if I extrapolate all the way over here, I'm going to end up with, say, 10 units of energy, okay? Units, and we're arbitrarily giving these arbitrary units, okay? My data is not as smooth, but my graph, the pictures I have are a little bit smoother. Now, if I were to take where the energy level of the reactants began and I extrapolate a little bit further, okay? And then I go from the top of the hill to that point, okay? That, and if I, go from the top of the hill to, say, the energy level there, that could be, I don't know, for argument's sake, let's just say 100 units of energy, okay? So that's 100 units of energy. That's 30. The difference between 100 and 30 is 7 units of energy. Right? Do y'all see that? Whenever we measure the difference, we always take the value of where we ended up minus where we started. And so in this scenario, we started off at 30 and we ended up at 100 on top of the hill. Okay. So the difference is 7 units of energy. That amount of energy we call the energy of activation. That is the minimum amount of energy for this hypothetical reaction of R going to products. Okay. Now, if I take where the products ended up and I extrapolate and find out where we started, obviously we started at 10 units of energy, but if I extrapolate where the reactant started and where they ended up, that difference right here between where they started and where they ended is we have we call that delta H. That is the energy of the reaction, which if we calculate that, we ended up, remember again, when we measure the change of anything, we take where we ended up minus where we started. We ended up at 10 units of energy and we started at 30. So 10 minus 30 is negative 20 units of energy. And that is what delta H is. That is the energy of this reaction, okay, negative. The fact that it's negative, delta H is negative, tells you that we have an exothermic reaction. Remember the terms exothermic and endothermic? In this case, this reaction gives off heat, okay? It gives off heat. And I put these numbers in here to show you mathematically that we got a negative value. But another way to look at this reaction and just looking at it, it's saying that the products energy level are lower, ended up in a lower energy value than the reactants. Therefore, I have an exothermic reaction because I'm going to have a negative value. Okay. One more position I forgot to put is on top of the hill. We call that TS. That is the transition state we talked about earlier in the first slide, where that is that point where you're getting bond breakage and bond formation. It occurs, very short time periods, very spontaneous, but that is the transition state. So we start off with where the reactants are. We go up the hill, okay, to a transition state. And then from there, we go down the hill to some energy state that the products finally end up. If the energy state of the products is at a lower value, lower quantity than where the reactant started, we end up with a negative value for delta H. Delta H is the amount of energy for this reaction. If it's negative, then it's exothermic. We will have an example where you have an endothermic process. And all that is the product ends up at a higher energy level. I'm going to kind of draw it here in a different color. So if you can imagine for a second, instead of ending up here, let's say ended up right here, okay? For this example. Well, you can see here that the energy level of the products ended up at a higher level. It's probably about maybe 50. We extrapolate from where it's at. Starting from 10, if we subtract 50 from 10, we got a positive 20 units of energy. The fact that it's positive tells me it's an endothermic reaction, endothermic, which means it gets cold, okay? So the main difference, and we'll have a better diagram here in a second, is that it's an exothermic, the product is a lower energy state than the reactants. If it's an endothermic, the products end up in a higher energy level than the reactants where they started, okay? So let's go back to this. So we got the transition state. You look in the top right tells you where the transition state is, okay? And that's that point in this reaction where bonds are being broken and bonds are being formed, okay? You can see there that the energy of activation, delta H is the difference between where the reactants are started off. Let me restate that. That is the difference between where the products ended up energy-wise minus where the reactants started energy-wise. So it's the product's heat or energy minus the reactant's heat. In this scenario, you'll end up with a negative delta H, implying that you have a exothermic process, okay? Exothermic. If you recall, when we had talked about endothermic and exothermic, the endothermic process, heat or energy is a reactant. It's taking energy from the environment. We end up with a cold reaction. And exothermic heat energy is given off. So we end up with a warm reaction, okay? All right, so looking at this graph, what you should be able to identify are what are marked there. What is marked? Where the reactants are, where the transition state is, where the energy of activation is, where delta H or the energy of the reaction, and where the products are, okay? The change of heat energy is delta H, also known as the energy of the reaction. Either one would work. Now, also identified by just looking at it, you can look at it and remember that when the product energy level is lower and ends up lower than where the reactants began, okay, it will have a negative delta H. And if it has a negative delta H, it is exothermic, okay? Here's an example where delta H is positive. The same the same areas to mark is where the reactants begin, far left. Okay, it goes up a hill to the transition state and then down to a state where the products are. Okay. The energy of activation doesn't change. It is the difference between the transition state and the reactance energy level. That's energy of activation. And this scenario, delta H, does change compared to this example. Okay. And the products are at a higher energy level. They end up at a higher energy level than where the reactants began. And if you do products minus reactants, you end up with a positive delta H, meaning it will be endothermic. Okay, so be able to identify these positions. Here's an example of endothermic process. Here we have them both together, okay? Exo on top, endo on the bottom. And like I stated, be able to identify those 1, 2, 3, 4, 5 positions on the table, and then also identify whether you're dealing with an endothermic or an exothermic process. Okay, what happens with a catalyst? Well, the most common effect of a catalyst is that it takes the energy of activation, and it's highlighted here in a darker line, and lowers it. And so maybe a reaction normally takes, a lot of temperature for it to occur. A catalyst will take it and lower that temperature, and that reaction occurs at a much lower temperature. Okay. And then once it's done, then just releases or just gets out of the way, and the reactants do their thing. So they don't do anything with the reactants. They do something to help the reaction, and then just don't get involved, and they're not incorporated into the products. They kind of go on their merry way, if you will. And catalysts could be very helpful. There's a number of catalysts that are used for reactions throughout the world, but they can also be very dangerous. I have an example myself. When I was a graduate student at the University of Kansas, I was working in the group that we studied peroxides, and there's a slew of peroxides out there. The only one, the one that you're probably familiar with is hydrogen peroxide, but that's only one of multiple peroxides. Peroxides have a key factor in mostly making polymers and all kinds of reactions out there. So my job was to study the thermodynamics, the kinetics of this reaction. And normally I would do that. I'll put a peroxide in tubes, sealed tubes, put them in a constant water bath temperature, and then periodically take a tube out, open it up, and analyze that tube for multiple things. And so I would do this over a period of time. And so I prepared some tubes, and I had about a dozen tubes with the solution, and I got them all together, sealed them up, put them in the bath, set it whatever, about 80 degrees, I forget. So it was pretty high, not too high, but warm. And I stepped away from the hood, and that moment, the whole thing went boom. It just blew up. It turns out that in washing these glass tubes, they had some residue iron, which I guess I didn't clean the tubes up very well. There was some iron, good old-fashioned iron ion that actually acted as a catalyst and caused the decomposition of my peroxide to occur very fast enough to cause a problem. But we learned something. We know now, we learned that we can use iron to help this reaction go a little faster. Namely, we were able to fix it so it won't occur so quick. So anyway, catalysts can play an interesting role in reactions. Okay, so that being said, guess what? I told you chapter 11 is short. You are done with chapter 11. Okay. And the next chapter it's even shorter. Okay. I kind of introduced this a little bit yesterday at the lab. We talked about the mole, and I explained that the mole is a very important concept when it comes to these calculations that we're going to be doing. Because when we talk about, grams of A reacting with grams of B, or figure out how many grams of product we made, I cannot go directly to grams and grams. I need to convert the moles, the grams into moles. And from that point, once I know the moles of A, I can go and figure out the moles of B based on the balanced chemical reaction. Okay, this is where it's quite important why we balance the reactions. So we talked about these reactions, these 6 different reactions. Now we learned about how to balance them. And now we're going to take these reactions and we're going to start doing calculations. Okay, this is the beginning of the how-to, but we have to introduce the mole. Now, what exactly was the mole? Well, the mole was brought into our knowledge by good old Avogadro. There's a picture of him on the right. Interesting looking picture here of Avogadro. Okay. And as I explained in the lab yesterday, that the mole is nothing more but a number, just like 12 equals a dozen. It just happens that this number happens to be very, very large. Now, the symbol for the mole is the capital letter M subscript A. So that's Avogadro's number. 6.02 times 10 to the 23rd, which, by the way, since you can see that number in scientific notation, we refresh your memory on how you do scientific notation on your calculator, because we'll be using it to do calculations. Okay. Now, how big is this number? Well, gives you an idea. Avogadro's number is 602 sextillion. Okay. If I take that decimal point, move it over, and write it longhand, 6 trillion has 21 zeros. You look at the far left. You can see 1 billion. A billion has 9 zeros. Okay, and there's other very large number like a googolplex down at the bottom. You got the centrillion has 303 zeros. Some of these numbers are just mind-boggling as far as how big they are. And these numbers in mathematics that can go to infinity. Now, I mentioned this briefly, and I said, well, how another perspective as to how large this number is. And a good way to look at it, if you were counting 1 particle per second, that's your rate, that's your frequency. Okay, 1 particle per second, you go 1, 2, 3, 4, 5, and you count until the end of Avogadro's number. Well, guess what? It's going to take 19 quadrillion years to be at the end of that number. That's how big that number is. Okay, humongous number. Now, another way to look at it, if you had 1 mole of softballs, softballs about a little bit bigger than a baseball. I don't know, maybe about 4 or 5 inches in diameter. Okay, if you had 1 mole of those, all those softballs together would be the size of the Earth. Okay, that gives you the concept of an idea how big that number is, and also keep in mind we're talking about atoms. And I also hopefully can demonstrate as to how small these atoms really are. Okay. Now, the mass of a mole of atoms is essentially when we're talking about the elements. And again, when we did this yesterday's lab, I explained that. I said that, for example, carbon has an atomic weight of 12.01 grams. Now, all the atomic weights have the units of grams per mole, okay? And so you can go to the periodic table if you're asked a question, well, if I had 2 moles of carbon, how much would that weigh? What do you think? I got 2 moles of carbon. How much would it weigh? What do you think? If 1 mole weighs 12.01 grams, what would 2 moles weigh?
2402.
You got it. Okay, exactly. And the same would true, that would be true for whatever element. You just look at the atomic weight. And if you ask you if they said, well, half a mole, well, how much would half a mole of carbon? Would simply half of 12.01. Okay. All right. So as I mentioned earlier, the mole is nothing more but a number. It is number of units or entities. So when we talk about moles, we could be talking about 1 mole of bananas, or oranges, or students, or whatever. But since we're dealing with chemistry, we're dealing with 1 mole of atoms, or ions, or molecules, or 1 mole of formula units like the compound sodium chloride, aluminum oxide, etc. Okay. All right. So to figure out how many grams in 1 mole, like I mentioned, the questions are asked, how many grams in 1 mole of carbon? Well, we simply look up the atomic weight of carbon, and carbon, is 12.01. 1 mole of gold weighs 196.9. See, I included the units there, grams per mole of the atomic weight. Sodium has an atomic weight of 22.99 grams. So 1 mole of any one of these elements obviously is going to weigh differently, right? Simply because every element has a different number of protons and electrons, and therefore going to have a different weight. Okay. Now, the thing about this is that all of these examples have exactly 6.02 times 10 to the 23rd atoms. Just like the analogy I used with the eggs, small, medium, and large, if you recall in the lab yesterday. I said the small eggs are 100 grams, medium eggs 200 grams, large eggs 300 grams per dozen. And so knowing that, if I have a weight of whatever size I'm looking at, I can figure out the dozen, or vice versa. If I know the dozen, I can figure out the weight. Okay, we're going to do very similar with respect to atoms. It's just that for some reason the concept of mole kind of seems to come out complicated. We're going to see if we can not complicate it. All right, now we have talked about we use the term molar mass. It's kind of ambiguous a little bit, but when we talk about molar mass, we're really talking about the compound as compared to the element itself. We're talking about the atomic weight. Okay, so we kind of use this simultaneously. When we talk about molar mass, we're referring to either the atom or we're referring to a compound. And here, they're asking you to determine the molar mass of barium hydroxide. Okay, so here's where it comes into play. That's why I have nomenclature. Nomenclature, we get the name, figure out the formula, got the formula, figure out the name. Here we have a name, we got to figure out the formula. Okay, so hopefully by now you can figure out the formula, and that's the formula. Barium is a +2. The hydroxide is a -1. So I need 2 hydroxides for every barium +2. So that is the formula. Okay. So now I need to calculate the molar mass. Well, no problem. Determine how many atoms I have of each. Okay. Analogous to when we did the Lewis dot structures. Remember how we looked at it and we say we have this number of hydrogens, this number of nitrogens, so on and so forth. Well, we're adding a step now. With that number of atom, we're going to multiply that by the atomic weight. Okay. And so here we have barium has an atomic weight of 137.33. Okay. When we deal with these atomic weights, please use the periodic table that we've been using throughout the semester. Yes, a variety of different periodic tables. use the atomic weights given there. This one's given up to given it to you in 2 decimal places. Using other atomic weights, they may go 3, 4, 5 decimal places, and that can mess up with your answers with respect to Canvas, okay? But if you stick with these, you shouldn't have a problem with Canvas. But also keep in mind too, yes, if you use someone else's numbers and your numbers are incorrect, I'll be more than happy to look at your answer, and if it's, what it should be, obviously I give you credit. All right, so barium has an atomic weight of 137.33, okay? Oxygen, there are 2 oxygens, each one has an atomic weight of 16. So we take 2 times 16, and then we have 2 hydrogens, each one with an atomic weight of 1.01 grams per mole, okay? There's 2. Do all that, tally it up. The molar mass of barium hydroxide is 171.35 grams per mole, okay? Now, if I weigh out 171.35 grams of barium hydroxide, how many individual compounds of barium hydroxide do I have? If I weigh out 171.35 grams, how many barium hydroxide compounds do I have? I have 1 mole, okay? What does 1 mole equate to?
The 171.35?
No. If you were to go to the lab and you weighed out 171.35 grams in the lab in the balance, that would be equal to 1 mole of barium hydroxide. How many particles, how many compounds of barium hydroxide would I have if I weigh out 171.35 grams? Okay, let me ask it this way. What if instead of the term mole, instead of dozen? Okay. And so its molar mass is 171.35 grams per dozen. Now, if I weigh out 171.35 grams of barium hydroxide, how many individual molecules would I have? How many in a dozen?
12.
12, okay. So obviously you have 12, right? If you weigh it out 171.35, if the molar mass had the units of grams per dozen, okay? But the units are grams per mole. Now, put your thinking cap on. If I weigh out 171.25 grams of barium hydroxide, how many individual molecules of barium hydroxide do I have?
It wouldn't be the same?
No, it would be 12. How many, what's the number for a mole?
1.
No. Avogadro's number is equal to 1 mole. 1 mole is equal to 6.02 times 10 to the 23rd. Just like 1 dozen is equal to 12. And when I put up 1 dozen here, I said a dozen instead of a mole. Everybody said, yeah, okay, if I weigh out 171.25, I have 12 molecules of barium hydroxide, which is correct, okay? But, and I was trying to, show an example here, but the units are not a dozen, the units are a mole. So if I weigh out 171.25 grams of barium hydroxide, I will have 6.02 times 10 to the 23rd units or compounds of barium hydroxide. Just like the previous example, when we were doing the individual atoms, when I said carbon had atomic weight of 12.01 grams per mole. If I weigh out 12.01 grams of carbon, I have 1 mole. Well, how many atoms of carbon would I have? 6.02 times 10 to the 23rd. Okay. You all see that? You know, if I replace that mole with a dozen, you know, if I said again, if I replace this with a dozen, and I replace this with a dozen, again, if I weigh out 12.01 grams of carbon, I have 12 atoms of carbon. If I weigh out 171.35 grams of barium hydroxide, I got 12 atoms of barium hydroxide. If the units were grams per dozen, does everyone see that? Okay. But the units are not grams per dozen. The units are grams per mole. And every mole contains 6.02 times 10 to the 23rd units, just like every dozen has 12 units. Okay. All right, well, let's go on. Okay, here's Avogadro's number. 6.02 times 10 to the 23rd atoms, moles, bananas, oranges, what have you, per units per mole. It is a ratio. I can't overemphasize. You hear me say a lot. You got a ratio here. I can write that ratio like I did on the left, or I can write it like I did on the right, with atoms, molecules, units in the numerator or in the denominator. Which one I utilize depends on the question being asked. Okay, so the first question says, how many calcium atoms are in 0.25 moles of calcium? Now we attack this problem like we did before with the unit conversion, okay? How we did those, we're bringing that factor label in here. No different, we're just going to be using different numbers. And the first step we did was what? We wrote down what we're given and we write down what we're looking for, okay? And so we are given 0.25 moles of calcium, right? And what are we looking for? We want to know how many calcium atoms, the number of calcium atoms. That's what we're looking for. So obviously we're going to use Avogadro's number, okay? Now question I ask you, which one am I going to use to multiply here? Avogadro's number on the left or Avogadro's number on the right? What do you guys think? Remember what you did here to figure out which one you're using? You keep track of your units.
The left?
And the left, exactly. Because I want moles in the denominator right here. Because I want moles to cancel. And then up on top is going to end up with atoms. So I want Avogadro's number would be the one on the left. That is correct. Okay. No different than when we did 2.54 inches or centimeters in 1 inch. No different than that. And if we started with 10 inches here, we wanted to convert to centimeters. That's how we set it up. Same process here. Keep track of your units. Okay. Once we do that, we got the following. Now we get, it's a quarter of a mole. So it's going to be a quarter of Avogadro's number. So that number you end up with sounds reasonable, 1.51 times 10 to the 23rd. Again, you're using scientific notation, so make sure you refresh your memory on how you do that on your calculator, because it's going to be pretty tough to type in, 6.02 and move that decimal point over. What did I say? 602, 6 trillion. Okay, so you got to convert that to scientific notation. All right, second one, calculate the moles of 7.75 times 10 to the 27 molecules of oxygen. In this scenario, you're given how many molecules of oxygen. You want to convert that to the number of moles. We're still dealing with Avogadro's number, okay? And in this scenario, same thing, similar, we write down what we are given, okay? We are given 3.75 times 10 to the 27 molecules of O2. We're going to have Avogadro's number here, and we're looking for the number of moles, okay? So which one am I going to use? The one on the left or the one on the right?
On the left again?
And sure, what units are we,
Okay.
what units are we
Oh,
looking?
okay, the right.
Exactly, we want units, moles in the numerator, okay? Let me bring the other ones a little bit better than my handwriting. Okay, notice we have the one on the right because we want the molecules, that MLCLS is shorthand for molecules. We want molecules to cancel, okay? Leaving us with units of moles, which is what the question asks. So if you have 3.75 times 10 to the 23rd molecules of oxygen gas, that corresponds to 6,230 moles of oxygen gas, okay? All right. Now this is calculations using Avogadro's number. And Avogadro's number is nothing more than a ratio, just like the atomic weight units are a ratio. Avogadro's number is 6.02 times 10 to the 23rd atoms per mole, like written on the left, which I can take that ratio, invert it, and now I have the one on the right, okay? The atomic weights, remember this, the atomic weights, for example, carbon had an atomic weight of 12.01 grams per mole. I can write it like that or invert it. 1 mole of carbon is equal to 12.01 grams. Okay, you can see that I'm going to be using atomic weights, molar mass in conjunction with Avogadro's number. So I can calculate Avogadro's number, which if I have a large number of atoms, I can convert that to moles. And then from moles, I can go to grams, okay? Much like the same thing we did with the unit conversions. We did the unit conversions where we maybe had inches to go to centimeters, and centimeters, maybe we went to meters, okay? Those type of calculations, and we set up the ratios properly so we keep track of the units. Okay, I can't overemphasize these ratios again. Remember that slide I had where I did this ridiculous conversion of dental hygiene students to bananas? Okay, and I did that on purpose to demonstrate that you can go from whatever units to whatever units as long as you have conversion factors and as long as you set up your units properly so the units are going to cancel. Keep it in mind that you write down what you're given unit-wise and you write down what units you're going for so you can have a roadmap of how to put these conversion factors together to get you to the units that you need, okay? This is the same thing. This just different units, that's all. This is the same thing. Okay, now, as I mentioned, the molar mass has the units of grams per mole or moles per gram, depending how you need and how you're working it. Okay, for example, question says here, how many grams is 1.667 moles of oxygen gas? Now, the key thing here is this. All right, we need the molar mass. We're talking about oxygen gas. Now, which oxygen are we talking about? O or O2?
O2.
O2, good, because it's oxygen gas. Now, the molar mass of oxygen is 16 grams per mole. But of oxygen gas, what would that be? What would be the molar mass of oxygen gas? Wouldn't that be 32? Because I got
Yes.
2, yep, grams per mole. Okay, and so when you see the problem and they're talking gas, make sure you're talking about diatomic. You got to remember the diatomic atoms. All right, so write down what we're given. We're given 1.667 moles of oxygen gas, okay? We're being asked to calculate how many grams that is of O2. All right, so we're going to use the atomic weight, the molar mass of oxygen, which we're going to use this one right here, 32.00 grams per 1 mole of O2, grams of O2. You notice that the moles cancel, leaving me units of grams, okay? So just a matter of, let me clear this up and we'll do the, right there. Notice the units, moles cancel, leaving me with units of grams. Therefore, 1.667 moles of oxygen is equal to 53.34 grams of oxygen, okay? So we need to learn how to convert from moles to grams. And notice what you did. When you have moles to grams, you multiply by the molar mass. We're going to learn if you want a grams to moles, you divide by the molar mass. Okay? Moles to grams, multiply, grams to mole, divide by the molar mass. Okay, here we're asked how many moles is 45 grams of silver. Okay, so let's work it here. We have 45 grams of silver. Okay, and we're looking for moles of silver. So obviously I need a atomic weight because we're just dealing with silver itself. We'll just call it atomic weight. We need grams in the denominator and moles in the numerator. Okay, so using the periodic table, I believe it's 107.87 for 1 mole. I got this from the periodic table. Okay. Here it is, 107.87. Notice my grams cancel. Okay. All right, let's take a 10-minute break. I forgot, I lost track of the time. Let's take a 10-minute break, then we'll come back to this, all right? Okay, I am back. All right, for these type of calculations, this is going to be, important when we get to chemical calculations. This is just the beginning of it, okay? And so what we're learning here in this example we just did with silver was to convert moles, grams to moles, okay? The previous one with oxygen, we went from moles to grams, okay? And as I mentioned, when you have moles of anything, you multiply by the molar mass to give you grams of whatever you're working with. That's shown there with the oxygen example. What's shown with respect to the silver example, when you have grams of whatever you're dealing with, you divide by the molar mass to give you moles of whatever you're working with, okay? All right, here's an example that says, all right, how many grams is 0.0554 moles of water? Okay, so we have to do a number of things here. Obviously, we need the molar mass of water, so we need to know the formula. Okay, well, we know the formula of water is H2O. Okay, we have one oxygen and 2.02 hydrogens, two hydrogens, so we got 18.02 grams per mole for water. So we need that information. All right, so we start off, write down what we're given, 0.055 grams, or excuse me, moles of H2O. Okay, we're going to have a conversion factor here, which would be the molar mass, and we're looking for grams. So we're going to set that up for grams of H2O. So knowing what we're given in moles and knowing what we're striving for with respect to the units tells us how we're going to set up a conversion factor. It has to be with moles in the denominator and grams in the numerator, because we want the moles to cancel, okay? That is up here, 18.02 is 18.02 is our molar mass for water. And simply now you do the math. Let me clear my mess and bring the other one in. Okay, so therefore 0.055 moles of water is equal to 0.9984. Okay, someday think about this. All right, we got water here. Its atomic weight, its molar mass is 18.02 grams per 1 mole. Okay, that means another way to write that is 18.02 per 6.02 times 10 to the 23rd molecules of water. That's a lot of molecules, right? So 1 mole is equal to 6.02 times 10 to the 23rd. And so when you go to the lab and you weigh out 18.02 grams, or it's approximately 18 cc's or 18 milliliters, that's not a lot. That's not a lot of water. And within that water, there's that many molecules. Now imagine for a second, not imagine, but calculate in your head or think about the amount of water on Earth. And then put that in perspective with how many molecules of water are on Earth. You know, and it just, the number is just mind blowing. It's astronomical as far as how many molecules of water are out there. And then if you try to think about the amount of water, whatever, 80, 90, 70% water in our body, imagine the number of molecules of water we have just in our body. Just amazing. It just boggles the mind, at least it boggles mine. All right, next one. Here's an interesting one because it's asking you to do this. It says, how many grams is 7.75 times 10 to the 16 atoms of potassium? Okay, so we're given the number of atoms of potassium. And now I can't go directly from atoms of potassium to grams of potassium. Remember, the middleman, the middle unit to get us from bananas to oranges is moles. So what I need to do is to convert the number of atoms of potassium to moles of potassium. Once I have that, now based on the atomic weight of potassium, I can go to grams of potassium. You see how that works? We have moles. Moles is our middleman. All right, so we write down, again, like we would do any problem, is we write down what we're given, okay? So we start off with 4. I don't know why my pen. 4.75 times 10 to the 16 atoms. Okay, we know that we need to use Avogadro's number, 6.02 times 10 to the 23rd, in this case, atoms per mole. Okay, atoms, molecules, bananas, oranges, what have you. Okay, and so we want to get rid of atoms, so that means that atoms will be in the numerator and mole will be in, mole will be in the numerator, atoms will be in the denominator. So our first factor would be Avogadro's number to get us out of atoms and into moles. Okay. Potassium, we need to look that up. Potassium has a molar mass of 39.10 grams per mole. So we need one more factor here, which moles will be in the numerator and grams will be in the denominator. What did I say? 39.10? 39.10 per 1 mole. Okay. Notice that our moles cancel, but our moles was the middleman because we had atoms here and we needed to go to grams. We cannot go directly. We have to go through moles. So we have to use Avogadro's number to go from atoms to moles, and then the atomic weight to go from moles to grams. Okay. So my units have been set up properly. I checked that off. Now it's a matter of you plugging your numbers in the calculator and getting your answer. So here it is, your 2 conversion factors. Okay, so first one gets us to moles, second one gets us to grams. So think about this for a second. 4.75 times 10 to the 16 atoms. That's a lot of atoms. And when you calculate how many grams that is, 3.09 times 10 to the -9 grams of potassium. Very small amount. The balances we have in the lab couldn't even weigh that. We have to get a special balance to be able to weigh that amount. Even in a small quantity of potassium, we have an extremely large number of atoms. Okay. All right. All right, so here's examples of going from grams to moles and moles to grams, and the last one is from atoms to eventually grams, okay? So we need to be able to both convert, use this factor. All right, now there's another factor here. Under what we call standard temperature and pressure, STP, which is 0 degrees Celsius and in 1 atmosphere. Right now, we're approximately 1 atmosphere, pretty our reference point. If we go, further up in the air, we have less atmosphere, our value goes down. If we go down, like into the water, we increase the pressure. We got greater atmosphere. But this is about 1 atmosphere where we're at now. And at 0 degrees, this is only for these conditions. Okay. Under these conditions of 0 degrees Celsius and 1 atmosphere, a gas occupies a volume, 1 mole of any gas occupies a volume of 22.4 liters. Okay. Recall back when we were doing the physical properties, we said the gas just occupies the volume of whatever container it's in. Okay, it doesn't really have a known volume. Well, here it does under these conditions and these conditions only. Okay, if these conditions are not met, then this is not true. This, by the way, is another ratio. 22.4 liters per 1 mole, or 1 mole per 24 liters. So here we go again. Our conversion factor, moles, are a common factor. So you think about it, if you're dealing with a gas and you start off with molecules of gas, you can convert 2 liters, or excuse me, 2 moles of gas using Avogadro's number. And then from that, using this conversion factor, convert that to a volume and calculate what the volume is of that gas at STP. Or instead of using this factor, use the molar mass and calculate the grams for that amount of gas. Okay. All right, let's go back to previous slide. All right, so note here what's happening. We have all these gases here. We have 1 mole of gas, of all these gases, hydrogen, fluorine, ammonia, etc. All of them have 6.02 times 10 to the 2030, just like you never had a dozen. Every one of these is 12. But we're talking about a mole, so we're talking about a big, big number. Obviously, each gas is a different molar mass. It's a different atom. So hydrogen has a molar mass of 2.02 grams per mole. Fluorine, 38.00 grams per mole, okay, et cetera, et cetera. What they all have in common at STP is that they occupy a volume for 1 mole, a volume of 22.4 liters. Okay. All right, 22.4 liters. All right, so with that information, now we have the conversion factor at STP of liters over moles or moles over liters. It's a ratio like we've been doing that we can arrange as needed. First example says, what is the volume of 1.25 moles of argon gas at STP? Okay, well, here's something to look at. Think about your number that you're going to calculate. You have greater than 1.1 mole, because you know that 1 mole occupies 22.4. You have 1.25 moles. That means your final number is going to be much greater than 22.4 liters. Okay, so that's a good way to see that your answer is in the right direction. What is the volume? We write down like any other problem. I hate to sound redundant, but I can't overemphasize that. Write down what we're given, okay, and what we're looking for, liters, and obviously we're talking about argon gas. And so we want liters in the numerator, moles in the denominator, okay? So it's 22.4 liters over 1 mole. Moles cancel. Okay, so it's 1.25 times 22.4 liters. And that corresponds to 28.0 liters. Now keep track of your sig figs. Sig figs are, we do that the whole semester. Notice here, 22.4 liters, that is a measurement. So that could play a factor in your sig figs, okay? Remember that, it's not an exact number. So this is a conversion factor that's a measurement, and therefore could play a factor in the sig figs. So we get a 28.22 liters, which is consistent with 1.25 moles. That we should expect a volume that's greater than 22.4. Okay, that makes sense. If you inadvertently divided that number, then obviously you get a number much, much less than 22.4, which should tell you, I don't think I did the math right. I'm going to double check my math. All right, the next one says, how many moles is 30.4 liters of hydrogen gas at STP? So if we have 30.4 liters, and we are at STP, I simply divide by 1 mole over 22.4 liters. So I have 1.36 liters, or excuse me, 1.36 moles of oxygen gas at STP, okay? All right, then here what we're doing is In the previous example, number 1 and number 2, the first number 1 example, we went from moles to liters. Number 2 example went from liters to moles, okay? The third example adds another step because we want to go from liters to grams. We want to know what the mass of 4.5 liters of chlorine gas is at STP. Okay, so the first factor converts us from liters to moles. Remember, just like in the previous examples we were doing Avogadro's number, where we went from atoms to grams. In order to do that, we had to go through the common factor, which is the moles, and we're doing that here. I cannot go directly from liters to grams without having to go through moles first, okay? So the liters of chlorine gas with the first factor is converted to moles of chlorine gas. Notice that liters cancel, leaving us with moles of chlorine gas. Then with the molar mass, this is the molar mass, MM, of chlorine gas. Keep it in mind that this is diatomic because it's talking about chlorine gas. They didn't say chlorine. If it was chlorine, then the molar mass would be simply the atomic weight of 35.45, okay? Yeah. But they're saying chlorine gas, and we know that chlorine is diatomic, so you got to double that. And that corresponds to 70.90 grams per mole, okay? So notice our moles cancel, leaving us with units of grams, which what we were looking for, okay? And so you just plug in those numbers in a calculator. And so 4.5 liters of chlorine gas would weigh 14.2 grams at STP. All right, this flow chart summarizes this, and we're going to have another flow chart much greater, but the common factor about this flow chart is moles in the middle, okay? Without moles, you cannot go in any direction, okay? So if you start off with grams and you need to get to volume, first of all, you have to be at STP. Let me clear this for a second. If you start off with grams and you want to get to volume, you have to be at STP, but you first have to get through moles. So, and to get there, you need the molar mass of whatever you've been given. So you need the molar mass of whatever chemical it is. And sometimes the molar mass is simply the atomic weight of the material, okay, and that's it. Or you have to figure out what the formula is for that compound. And then from there, add up all the atoms that are in that formula to figure out the molar mass. From there, you go to moles, okay? Then from moles, now you get to volume, okay? Using this conversion factor here of 22.4 liters per mole. If and only if, I can't overemphasize that, you are at STP, 0 degrees Celsius and 1 atmosphere pressure, okay? Or using Avogadro's number, you can actually go from grams to atoms or ions or whatever you need to calculate. But as the case down here, as the case was to get down to the yellow volume, you have to get to moles to get in that direction, okay? Now, this is not a one-way street. You can go in both directions. I could start off with units of ions and go all the way to volume, but I gotta get to moles, Or alternatively, I can start with the volume and work my way to grams. But again, I got to get through moles. Okay. It's the direction here. Let me clear this up. It got too messy. The direction here is both ways. I can go that way. That's a double arrow. Okay. But it must be through moles. Okay. Without moles, I can't do anything. And this is just part of the flow chart you're going to utilize. We're going to have another flow chart. We're going to incorporate together all this. And that flow chart summarizes how to get from point A to point B in all your calculations. Okay. All right. Example. Question says, how many grams does 17.4 liters of neon gas mass at STP? Okay. So how many grams does 17.35 liters mass? So which direction we're going? We got a volume, which is 17.35 liters, and we need to know how many grams. And so we are going from here to moles first, then to mass. I went too far. We can clear this up. We're starting at volume, but we got to get to moles. Once we get to moles, then we go to grams. Okay. All right. Let me clear my stuff out here. And then the second part says, how many atoms is this? Well, from volume, we're going to the right, volume to the far right. We want to go to atoms. So the first question takes us to the left to grams, and the second part of the question takes us to the right. Regardless, left or right, we got to go through moles, okay? All right, so number one is we write down what we're given, 17.35 liters, and we write down the units that we are striving for. Right? Unfortunately, I also wrote down the answer, okay? So anyway, first factor is converts our liters to moles of neon gas. Okay, so notice that liters cancel out, leaving us with moles. And then the second factor is the atomic weight of neon gas, which we get from the periodic table of 20.18 grams per mole. And that gives us the number of grams of neon gas at STP that has a volume of 17.35. The second part of the question is we start off with the same volume, 17.35, but we're trying to get to atoms. Again, we need to convert to, yeah. One second, please. I'm trying to get my phone. She likes to play games on it. Here you go. Go. All right. So the second part is we start with the same volume. Our conversion factor to get us 2 moles, and then we use Avogadro's number to give us the number of atoms. Okay. All right. So to rehash that from the flow chart is the first one. We went from volume over to grams, and the second part we went to volume over to atoms. Okay, but again, I can't overemphasize. We went to moles. Okay, went to moles. That's why moles is a very important concept that really needs to be grab a good hold of. Okay. All right, so now we're almost done with this chapter. Density, we talked at density before, where density is simply a ratio of mass and volume, okay? Now we're dealing with, we can calculate the density of a gas at STP without having to measure anything. Because the density is simply the molar mass divided by the molar volume, which is simply the molar mass of ammonia is 17.4 grams per mole, okay? 1 nitrogen, 3 hydrogens. And we know that the molar volume at STP is 22.4 liters per mole. If you look at that, we look at the units you end up with is grams per liter, okay? Which is not the normal units we use for density, which was grams per milliliter. But for gases at STP, normally those are the units of grams per liter, which is mass over volume, okay? All right, pretty straightforward in that if you need to calculate the density of any gas at STP. If STP is not mentioned, you cannot do any calculation. And that is true for these calculations. If STP is not mentioned in the problem, you cannot calculate the volume because it's only true that 22.4 liter per mole is only true when you are at STP. All right. Percent composition, we kind of introduced it. We did yesterday in the lab, okay, where we're looking at, in our case there, we took the total mass of the zinc and the chloride and then calculated the mass percent. Well, we can do the same thing here, similar, a little bit different because what we're doing is we have the formula and then we calculate the molar mass. And then basically what we do, we divide the individual contribution that every atom brings divided by the total mass, the molar mass, times 100, and you get a percent composition. For example, this one here, water, H2O. H2O, obviously, water here, you need the molar mass. So, and if you need the molar mass, you also need the formula. So, whatever you're going to calculate the percent composition, you got to have the formula. So we have H2O. And so we know that that's the formula for water. And the total molar mass for water is 18.02. Then we look at each element. There's 2 hydrogens. Each one is a total contribution of 2.04 grams per mole. We divide that by the total molar mass times 100. Hydrogen is 11.2% in water. We do the same for oxygen, 16 divided by 1802, which tells us that we calculate that oxygen contributes 88.79% percent. The total should add up close to 100. Sometimes like 99.9, but that's okay. Okay, so that is the percent. The chemical percent composition of water. And that is true for water found here or out in space someplace. H2O has that percentage, okay? Now we should be able to do that with any compound. And let's try this one, TNT. Anybody know what TNT is? You light it, what's that?
I said no.
Okay, when you light it up, it goes boom. Does that help? Dynamite, TNT, trinitrotoluene, aka dynamite. A side note here, there's a prize is given out every year for peace, a prize for medicine, for chemistry, for physics, for literature. Anybody know what that prize is? Nobel Prize. Nobel is the one who invented or synthesized TNT, which was, and then from that, once he made that, then obviously he created his millions and then created the Nobel Foundation and with that money. And now we have all this prize that we give out to scientists throughout the world and non-scientists. Anyway, to find out the percent composition, what we do is we first tally up, determine the molar mass. We have 7, identify how many atoms we have of each. We have 7 carbons, 5 hydrogens. How many nitrogens do we have?
3,
3, yeah. And how many oxygens?
6.
You got it. So with that information, we can now tally it up and figure out the molar mass. So we got 7 carbons at 12.01. That's a total of 84.01. 5 hydrogens at 1.01, total of 5.05. 3 nitrogens for a total of 42.03. And 6 oxygens for a total of 96.00, which gives us a total molar mass of 227.15. Now, we go through each contribution of each atom divided by the total molar mass and times 100. So carbon, 84.07 divided by 227.15 times 100 gives us 37.01% carbon. And hydrogen consists of 22.2% hydrogen, nitrogen's 18.5%, and oxygen's 42.26%. Now, as an organic chemist at Synthesis, we used to synthesize compounds. After we made them and we go through other instrumentation to check it, we send a sample, we clean it up, make sure it's as clean as possible it can be, send it out for analysis, and that's what they did. You tell it, I need to know the percentage of carbon, hydrogen, etc. And then that bit of information coupled with everything else that we have about it, if it is the correct percentage, then that adds to the conclusion of that compound is what you think it is. Okay. All right. So with that, try these at home. We can talk about them next time. We have how many liters will 3.425 grams of carbon dioxide gas occupy at STP? You should come up with 1.74 liters. Okay, set the problem up and see if you can come up with that number. Number 2, how many molecules are in 3.425 grams of carbon dioxide? You should come up with 4.65 times 10 to the 22 molecules. And finally, how many grams will 3.0 times 10 to the 15 molecules of carbon dioxide mass? That number of molecules of carbon dioxide should have a mass of 2.2 times 10 to the negative 7 grams. Okay, I'll leave this up for a little bit so you can copy it if you need to. But it's also on the PDF of the slides, so it's there. And we can take a look at it next time, or even in the lab time period if you need some help in the calculations. Okay. All right, congratulations. You are done with chapter 12. Now, I need to check something real quick. Bear with me. Okay. All right. The exam number 4 is scheduled for Wednesday next week, okay, which covers chapters 10 through 12. Given that the holiday is Tuesday, what I'm going to do is move only that exam, move that exam over to Friday. Okay? So I'm gonna change exam number
Or next
4.
week?
Huh?
Next week, for next week?
Yeah. To give you a little time, I don't mean Friday, I meant that Thursday. I'm gonna move it one day. That would give, that would give you, I don't want to move it to Friday because now you got exam number 5 coming up. That gets,
Okay.
gets a little, might put you in the bind. But
Okay,
because,
until Thursday?
yes, Thursday. So I'm gonna move it forward one day because of the holiday. I totally forgot about July 4th on Tuesday.
Are we still having lab Wednesday?
Yes,
Okay,
yeah, we'll have classes until the 19th. The 19th is our last day. I'm looking at, let me stop the share here and show you where we at. Okay, so exam number 4, which is chapters 10 through 11. Hold on one second. Let me do something here.